In this video, we're going to continue to learn about the concepts that we introduced in the first half of the quantum computing and reversibility lecture. So we learned that quantum computing must be reversible, but that's not the case with classical computation. So in some cases, we have reversible operations, such as with the classical NOT gate, but other classical gates are not reversible. So we're going to introduce a building block of classical logic, and that is the AND gate. So the AND gate has two inputs and one output. The output of this gate equals 1 if and only if both inputs are equal to 1. So let's check this out. If we have two inputs equal to 0, we get an output of 0. If we have a single input of 1, output of 0. And if we have two inputs equal to 1, we will get an output of 1. So this logical AND gate, is it reversible? No. That's because we cannot determine what the input was if we're only provided with the output. In the case of if the output is 1, we know that AND gate functionality says that both inputs are equal to 1. If we get an output of 0, however, we don't know what those inputs were. We can reason about those inputs and say that we know 1 is white, 1 is equal to 0, but we don't know which one that is. To be reversible, we need all outputs to have unique combinations. And we need at least as many outputs as inputs. So what is reversible? Reversible operations must have an equal number of inputs and outputs. So we saw this with our C0 demonstration and swap operation demonstration. So here, we're going to try to see if we can give the AND gate the same number of outputs as inputs to make it reversible. We'll start by first passing through the first or top argument from in to out. So here we have the 1 passing through and the 0 passing through. And then our second output, so the bottom output, is going to be equal to the AND gate's original output with the inputs values. So here we have 0, 0, 0, and 1. So 1 if and only if both inputs are equal to 1. So we have a little problem here. Even though our function has the same number of outputs as inputs, we have two choices that have the same output. Therefore, we don't know if we observe a certain output, what that input combination was. So it's impossible to get a unique output with only two inputs and outputs while if we want to preserve the AND gate functionality. So we're going to fix this in the next video. Let's just make an arbitrary function. We'll call it foo, and we'll check to see if it's reversible. So we have 4 unique input combinations and 4 unique output combinations. So far, everything seems to check out. So we'll make a visual truth table from the information on the previous slide. So this is the foo functionality here. And we can see that if we have an output of 1, 0, or black ball, white ball, we can map that to our input from our truth table. We have a different output for each unique input, and the input and outputs are the same size. So here we have a reversible function. Now that we know it's reversible, let's check to see if it's its own inverse, just like C0 and swap were. So we'll start by taking 1 and 0, so black ball, white ball, passing it through. We take our value from our truth table, we'll map it back to the output. So we have a ket 1, 1. And if we take ket 1, 1, pass it back through foo, so we have 1, 1, we result in the ket 1, 0, the original input. So when the output is sent through foo again, the original input results. This means that foo is not only reversible, but it's its own inverse. You can try this out with all the different input and output combinations to confirm. So we have all the values from our truth table, and we have them drawn here as well. And we can determine what our input-output combinations are. So we have 0, 0, 0, 1, 1, 0, 1, 1. And we can find the values for a matrix by looking at the visual representation of the operation. So we have 0, 1, 0, 0, 1, 1, 1, 0. And then from those values, we can fill in all the columns for our matrix, going from bracket notation to vector notation. To conclude, we learned that quantum operations are reversible so that no information is lost. Many operations we've learned about in class, such as the NOT, swap, H-gate, C-NOT, are known as self-inverse. So what does this mean? This means that we can recover our original input if we use that gate twice consecutively. Many operations that we're familiar with from classical computation are not reversible.